Number 13, now we're doing the population variances. That's the one where we calculated the F statistic and we used the variance squared of 1 over the variance squared of 2 at the very end of homework 18. So, on this one, an examination in psychology has been taken by both psychology majors and by some students from other majors. It is widely believed that the scores for both groups are normally distributed. A random sample of 29 examinations completed by psychology majors and an independent random sample of 23 examinations completed by students from other majors are selected. Among the sample students, the psychology major scored a mean of 526.6 with the important number, the variance of 10,140.49. And the students from the other major scored a mean of 501.5 with a variance of 15,276.96. Can we conclude at a 0.1 level of significance that the population variance of scores of a psychology major is less than the population variance of scores of other majors? So on this one, when they do these, it's going to look kind of weird. They're going to have the population variance of 1 divided by the population variance of 2. If I have the same number over itself, I'm comparing it to 1 instead of comparing it to 0 like we did with the differences. And so in this case, we want to know, can we conclude that that is less? If I'm just doing the less, that's my alternative hypothesis. So is my variance for 1 compared to my variance for 2 less than 1? I could draw. This one then would be greater than or equal to. So here I'm doing a one-tailed test. I am doing less than, so here would be where my alternative one is. There's where my null is. The type of test statistic I'm doing is my F test. And on my F test, I have to have my degree of freedom in my numerator and my denominator. My degree of freedom in my numerator is N1 minus 1. So 29 minus 1 would be 28. My degree of freedom in my denominator is N2 minus 1. N2 was 23. 23 minus 1 is 22. So I'm going to have my degree of freedom in my numerator as 28. My degree of freedom in my denominator is 22. I'm going to just find the value of my test statistic by dividing out my 2 sample variances. So I'm going to take the 10,140.49 divided by my 15,276.96, and that's going to give me the value of my test statistic. So that one's a lot easier to calculate than most of them have been. So when you divide 10,140.49 divided by 15,276.96, what do we get? 0.664 then. Okay? We're doing the p-value. On the Alex calculator, when you do the p of f, is it a greater than or a less than? It is a greater than. We're checking less than, which means we have to do 1 minus the p of f is greater than 0.664 because we're going the opposite way of what the calculator does, right? So if you do 1 minus p of f is greater than 0.664, whoops, I forgot my degrees of freedom. Degree of freedom in my numerator, 28. Degree of freedom in my denominator, 22. I tried to forget those last time, too. 0.152. 0.152. We're testing the p-value, so we're comparing it to the level of significance. Our level of significance that we are checking is 0.1. So 0.152 compared to 0.1 would be greater than. If it's a greater than, we are going to accept the null. This is my true statement. This is not true. So, can we conclude that the variance is less than? Can we say this is less than? No, because that was the not true statement, right? No. That was the not true statement. We just got 2 more here we're going to go through quick. All right, these ones don't take a whole lot of time anyway. So, again, on this one, actuaries use various parameters when evaluating the cost of life insurance. The variance lifespans of population is one of the parameters used for the evaluation. Each year, the actuaries at a particular insurance company randomly sample 20 people who died during the year, with the samples chosen independently from year to year, which means here N1 is going to be 20, over here N2 is also going to be 20, because they do 20 of them each year, right? The first row gives the sample mean, the second one gives the sample variance. Assume the lifespans are approximately normally distributed. Can we conclude at a 0.5 level of significance that the lifespan for the current year differs from the lifespan for the last year? So in this case, when we do differs, our null is going to be equal, our alternative one not equal. So we're going to have that weird fraction again. My variance of 1 over my variance of 2 is either going to equal 1 or not equal 1. The variance of the first divided by the variance of the second either equals 1, or the variance of the first divided by the variance of the second does not equal 1. The type of test we're going to do, an F test, and then we've got to do our degree of freedom. So my degree of freedom in my numerator, 20 minus 1, which is 19. My degree of freedom in my denominator is also 20 minus 1, because each year we did 20, so it's 19. So, degree of freedom in my numerator, 19. Degree of freedom in my denominator, 19. I'm now going to find the value of my test statistic. To find the value of my test statistic, I'm going to divide my variances. So I'm going to take 59.29 divided by 136.89. .433. Okay? We are doing a two-tailed test on this one, since we're doing an equal and a not equal, right? So, if we do, I'm trying to remember if I get the same number when I do both ends. No, I think I have to do minus. Because this one we are doing F is greater than. Let's just try it. I'm curious now. If you do P of F is greater than 0.433, whoops, I got to put my degree of freedom on there. Degree of freedom in my numerator being 19 and degree of freedom in my denominator being 19. What do you get for your number? Nope, that wasn't the right number. Okay, I do have to do the minus in there. I have to do the 1 minus in there since I'm doing the greater. I was thinking maybe I'd get the same number, but I don't. So do 1 minus P of F is greater than 0.433 with my degree of freedom of 19 in my denominator and my numerator. All right, so what I'm really getting there, 0.038, is the percent in the left side since I did 1 minus this value. The percent in the right side should be the same number. Whoops, 0.038. The percent in the right side should be the same number. I was hoping we could just do the first one, but we have to do the left side, so we have to do 1 minus. Since those 2% are the same, I can either add them together or multiply by 2 to find my p-value. So 0.038 plus another 0.038 would give me 0.076. I am then going to compare that to my level of significance. So 0.076 compared to 0.05. Is that less than or is that greater than? It is greater than. And if that's a greater than, we are going to accept the null. So this is the true statement. This one is not true then. So the bottom that you can't see on mine says, can we conclude that there is a difference? Can we conclude there is a difference? No, because the not true is the not equal, right? The true statement is that they are equal. So no, there is no difference. And quickly, although we're a little over time, let's do the last one so we have it done. All right. A psychologist studied the alcohol consumption patterns of 2 people in 2 age groups. One group consisted of people aged 21 to 35, the other people 36 to 50. The psychologist interviewed an independent sample from each group. She assigned a score from 0 to 100 to each individual. 0 meant no alcohol consumption, and the results are summarized below. So here, 27 people were surveyed, here 20 were surveyed. So, first of all, we want to know, assuming that these are approximately normally distributed, assume for the same scores of all people, can we conclude at the 0.5 level of significance that the variance for people from 21 to 35 is greater than the variance 36 to 50? So my greater than is going to go for my alternative hypothesis. So my variance from my first divided by my variance of my second is greater than 1, or for my null, the variance of the first divided by the variance of the second then would be less than or equal to 1. Which means we are doing a right-tailed test. Our type of test statistic, we're doing the F test, and we have to find the degree of freedom in the numerator and the degree of freedom in the denominator. So my degree of freedom in my numerator, 27 minus 1 would be 26. My degree of freedom in my denominator, 20 minus 1, which would be 19. We need to find the value of our test statistic. And so we're just going to take our variance from our first divided by our variance of our second. 225 divided by 118.81. 1.894. This time we're doing the critical value instead of the p-value. For the critical value, we use the subscript one. So we're going to use F sub. And since we're just doing a one-tailed test, we use the number that's there. If it was a two-tailed test, we'd have to divide that by 2. But in this case, it's a one-tailed test. So 0.05, degree of freedom in the numerator of 26, degree of freedom in the denominator of 19. .098. So that means 2.098 is our critical value, divides our normal curve in two parts. We want to check where that test value falls. Again, the greater than is my H1, the less than or equal to is my H0, my null. So, does 1.894 fall or be less than or greater than my 2.098? My 1.894, is that less or greater than the 2.098? It's less than. It's going to be over here on this side then, right? 1.894 is smaller than 2.098. That means that the null, the less than part, is true. This is my true. This one then would be not true. Again, I cut off the bottom, but you have your paper. Can we conclude that the variance for the 21 to 35-year-olds is greater than the variance from the 36 to 50-year-olds? Can we conclude it's greater? No, because that's the not true section, right? The greater was not true, so no is the answer to the bottom question that you can't see. All right. We